All right, good morning, folks. So our first talk of the morning is our very own Gray Nearing. He was one of the original founding members of the ITES group. So Gray got his Gray's background is in math and philosophy and hydrology. He did his PhD with me at U of A. Then he spent some time in academia and now is with Google. He spends a lot of his time wandering around the world from one Google office to another. So he has very interesting insight into the relationship between industry and academia, and in particular in the context of large-scale machine learning. So, thanks.
All right. So I've said this to anyone that would listen. I don't actually have anything to talk about today because I don't actually do research anymore. Almost none at all. Freddie can attest to that. My project deadlines are all like months and months overdue. And so I don't really have anything interesting to say. So when Uwe asked me to come talk here, I kind of was going to say no because I didn't want to bore you all, but I also didn't want to say no to this kind invitation. So what I'm going to do here is ramble a little bit, and my hope is that we can chat a little bit. I hope I didn't put too many slides, and of course, once I started putting slides in, there's like more and more slides and more slides. Okay, so people that don't know me, what I like to do is come in and say something ridiculously absurd, and because I'm a contrarian at heart, and try to get people to argue with me. And so we're going to try to do this a little bit, and I've kind of teased a little bit of this yesterday. And I think everyone agrees with me, so it may not go according to plan. So feel free to go get I'm not sure there's any value to this talk, so feel free to go get breakfast while I talk. So yeah, so the first thing I want to do is tell you about two experiments that were run in the last decade, meaning in the 2010s, two experiments that I really like. One of them that I did, but so I shouldn't say that I really like them, but the one that I did, I like a lot. Anyway, it doesn't matter. This is a set of experiments that was led by Martin Best at the UK Met Office. It was published in 2015. There was a whole, it was a pretty long author list, especially at the time. And the experiment was really simple. Martin Best and Gab Abramowitz, who's at University of New South Wales in Australia, they really put this together. And they took 20 FluxNet stations around the world, can't see my pointer, but 20 FluxNet stations around the world, and they measured the ability of the models, this is purely prediction, to predict sensible and latent heat flux. And they compared their models, these land surface models, which I'll just tell you about in a minute, but they compared the family of land surface models with a one variable instantaneous regression, a two variable instantaneous regression, a three variable instantaneous regression, and then some really simple conceptual models, a Manawi bucket and a Monteith model, and they're just trying to predict sensible and latent heat flux. And then they compared the skill of these models at all 20 sites, and they ranked them. So 1 is best, meaning if you had a score of 1, you'd be the best model at all 20 sites. If you had a score of 6, you'd be the 6th best model at all 20 sites. And these models are all basically at the time of 2015, these are all of the major land surface models that were operational in the world. This is Cable. It's been years since I've really looked at this, so I probably can't tell you what organization runs all of them. Cable is CSIRO. Maybe I'm getting this wrong.
I think you're right. Yeah.
CHTESL is the European ECMWF. COLA is a public-private partnership in the United States. ISPA is France. Jules is the UK Met Office, and then Mosaic and NOAA were run at NASA. Those were the ones that NASA runs. NOAA is public model in the United States, and then ORCHD, I forget. But anyway, the point is that this 3-variable regression model with no state space, no memory, just an instantaneous model taking 3 atmospheric variables, predicting sensible and latent heat flux, performs significantly better than all of the land surface models. All of these models are really 8 or 9-figure investments over the course of their lifetime. These are represent huge amounts of human activity going into these models. They were beat by, this is just a regression, it's a spline regression, so it's not sometimes I like to say this a little hyperbolically and say that we can beat the land surface models by drawing a line on a piece of paper, but actually you have to draw several lines to get there. Okay, so that's the first experiment I want to tell you about. The second experiment I want to tell you about is just this really toy problem that I did when I was working with Hoshin as part of my PhD. Okay, so we took a conceptual rainfall runoff model with a Nash cascade, a slow flow tank, and a nonlinear soil moisture component, and we can kind of think about this as a PDE, right? We can solve this. We can pretend like this is a PDE, or we're pretend like we're solving a PDE in sort of discrete time. And we can know that the PDE is not perfect. And so we can think about, okay, so what happens if we add a component to this PDE? So this is now, sorry about the weird graphics, this is now one PDE so that the solution contains some other function that is learned from data. Okay, so we have a PDE we have the PDE that's now one component that's, some conceptual model and then some correction component that we're going to learn from data. We're going to kind of learn this portion of the PDE, and I'm not going to tell you how we did it, like how you learn it. We used some expectation maximization algorithm that existed in the literature at the time, but we did it, and don't look at the plots. These are just there to remind me to tell you that basically after you perform this, we call it system identification. After you add this component to the model and you perform this database sort of learning procedure, this machine learning procedure to learn the correction component of the PDE, you get better results. So this is mean squared error. So you get better results than you do from data assimilation, parameter estimation, or nothing at all. This is trivial work, right? So, and the key here is that you have okay, so I'm going to explain the plot. The key here is that you have a period where you have data, and so you can run data simulation over a period of time where you have data and you can get really good results. So you correct the state space of the model in real time. But if you can't run data simulation over a period of time where you don't have any data. But if you run this sort of expectation maximization algorithm, which uses a Kalman filter as one of its components of the learning algorithm, you can actually store the information that you learned from data simulation and get better predictions sort of out of sample. Okay, so that was the experiment here. And you can look at the response surfaces of the model after you do this. So this is the original conceptual model. It has all these different states. And you can kind of look, you can only plot the relationships between any three states at once because we only have 3 dimensions to work with on the 2-dimensional screen. But let's look at the relationship between the quick flows, 2 of the quick flow states, and the slow flow states. So on this diagram, what is the actual relationship between the quick flow states and the slow flow states? There is none. So the original model, there is no direct relationship because they're not connected. They're only connected through some causal pathway that's in the history. They're not directly connected. But after you add that learning term, you see that there is actually a relationship. So the value of the quick flow states actually tells you something, actually feeds it, and it doesn't just tell you something. This is not just the probability distribution, this is actually the functional response surface. So the quick flow states actually have some pathway to send information to the slow flow state. So what this correction term did is it kind of learned something that was wrong with the model in a way that allows the model to behave sort of fundamentally differently. And if you look at this, I think any hydrologist will tell you this makes sense. If you have some overland flow or you have some Beto zone flow, however you want to interpret the Nash cascade, it will feed into some sort of longer memory reservoir in the system over time, right? So we learn something about the model and it makes sense. Okay, so that's the second experiment. The last thing about this second experiment that I want you to know is that I'm really not going to explain this, but the last thing that I want you to know is that if you just take the machine learning component of that PDE, just do a machine learning model, you get significantly better predictions than any of the other models we talked about, including the one where we added the machine learning component to the state space model. So the machine learning model alone performs better than everything else by a large margin, okay? So here's my question for you. Which of these experiments is more interesting? Which one do we build on going forward? Which one excites you more? Okay, I'm asking this because I've given this presentation that covers these 2 experiments maybe 100 times. That's probably an underestimate, and many of those for job interviews. And so I've gotten a lot of feedback on which one excites me more. I'm really curious which one of these is more interesting, which provides a better foundation for science. Who votes number 1? Who is more excited that we built machine learning models that beat the best physics-based models that we have. And who's more excited about using machine learning to learn specific deficiencies in our models? Okay, that's half and half. So I don't know, it's impossible to do a counterfactual in time with real people, but I will tell you that when I present this, this is the one that gets all the attention. I've presented this for 5 or 6 years now. And for me, it's much more, the first experiment is much more interesting. It's much more interesting for me to discover that we have a lot of information in our observation data that's not being captured by our models. I think that is a revolutionary discovery in any field of science. The fact that we have tools that allow us to discover that is just, it's absolutely fascinating, and it provides sort of infinite possibilities for improving what we're doing. This idea of actually going into the models that we build and finding out what's going wrong in specific models, I think that's probably the most boring thing that I could possibly imagine. I don't care about your models. Okay? Remember, this is a lot of hyperbole. I'm trying to make fun of you guys. Okay. So what's a model? Okay, so this is something that Hoshi and I published a long time ago. This is some people think about models like this. I don't want to prescribe this belief to anyone except for me back in 2014. So what is a model? You define a boundary condition, you define a control boundary, you define some boundary fluxes, usually fluxes, let's just say oftentimes, although this is definitely not even remotely true, oftentimes the boundary fluxes that are normal into the boundary are data that you have as inputs, and boundary fluxes out of the boundary are data that you want to predict. Those are the things you want to predict. And we can go further and we can kind of define a control volume that contains several mini control volumes. And so we kind of understand, this is sort of like where we think about the causality of what's going on in the system, and we define little components, and we talk about how each of the components sort of has some sort of causal relationship with other components, and usually those causal relationships are represented by mass or energy fluxes or whatever, entropy fluxes, if we want to get really creative. Okay, so, but this is not a model, right? This is a tiny component of a model. There's no model that's ever been built in human history that looks anything like this, ever, right? This is a model, okay? A model has sort of two fundamental things to it. It has some chain of events that happen between two pieces of data. No way around this. All you have is data, there's nothing else. You have some mental conceptualization of what's going on. That's this component right here, and I've made it really big so that you're sure to see it. But how big is this in terms of the effect that of the information, in terms of the effect of so we have an information flow from our input data to our response data, and there's the information flow is determined. Let's just stick with the classic like information theory probability paradigm of some philosophy of science. So this information flow can be defined or explained sort of completely by conditional probabilities, which we can then integrate, take log transforms of whatever we want to do. And how much influence does this particular component, this particular marginal probability distribution that defines our, let's call it epistemic uncertainty, although I hate that word more than life itself. So how much does this this probability distribution influence the chain rule that's going to get us the eventual conditional probability distribution over the output data? And notice that when we do science, what we're really talking about, the scientific method has a very like sort of well-defined role in this picture. Sometime you're going to get a prediction. It's going to be an uncertain prediction, and the scientific method is saying, what does my prediction look like? How does my data compare against the prediction I'm making? I don't personally know of any, philosopher or scientist that's framed the scientific method that doesn't include some type of prediction against testing a prediction against an observation. I'm not aware of any interpretation of the scientific method that doesn't fundamentally involve that. So where does information come from? This slide has nothing to do with my point, but I just want to make sure that we use the word information in this talk. There's really two types of information in this scientific method. One is we have inputs. These are the perturbations to our experiment. We're talking about a pegboard experiment in some physics lab somewhere. And we have, but all experiments in all of human history also, where we have some perturbations which are measured, and we have some experimental response which is measured. The perturbations to our experiment have some information about the experimental response. That information is sort of interpreted by some true physical, some algorithm that is the real world. And then we also have information from our model predictions. This is our attempt to emulate this algorithm with some set of theories that we turn into models. And then we have some model predictions, and those model predictions contain information about the experimental response. And all hypothesis tests, I don't know if this is true or not, but I can't think of an exception. Probably there are some. But we can kind of think about hypothesis tests in this very, very broad, very undefined, very imprecise way as sort of measuring the relationship between these two information flows. We can say how much of this information, I'm sorry, how much of the information that's defined by the true physical relationship do we capture by the model relationship? I think you can frame most hypothesis tests from this sort of perspective. Yeah. Okay, I don't remember what I was going to say there. Okay, oh yeah, okay, so sorry. I made this slide deck yesterday on the airplane. Okay, so the point I'm trying to make here is this. So even if you like this idea of taking data and using it to find specific deficiencies in our models, you're doing something that is fundamentally different than what we've done with models in the past, right? So if you have a learning algorithm, so we have this thing where we use these data-driven models in earth science. They're black boxes. People have trouble interpreting them. People have trouble understanding them, and we don't learn a lot from them, right? At least you've all heard this way of thinking about data-driven modeling, right? Okay, so one of the things that can solve this is you can either look into the black box, see what it's doing, and try to interpret what it's doing. So you can try to make black boxes that have this sort of internal structure in them, and so you can sort of explicitly define all these causal relationships and kind of learn all the relationships between those different subcomponents of the system. Or you can get your machine learning algorithm to learn relationships in the system that you didn't hypothesize, right? You can actually get it to learn things that are going on, information flows in your system, or that it thinks might be in your system that you didn't hypothesize. And the point that I'm trying to make with this sort of explaining my interpretation of the scientific method is that that's something new. So when we build models that represent our conceptual understanding of systems that contain causal relationships, that contain mass and energy fluxes explicitly in the units that we're familiar with, the kind of hypothesis testing we can do basically boils down to sensitivity analyses, right? We can perturb things and we can measure the information, whether we can predict what happens when we make those perturbations. And in that sense, all hypothesis testing works on black boxes. You can look inside and you can say, I understand this and this, what's happening inside a model here and here. I understand the information flows because those information flows are expressed in units that I'm familiar with. But, and here's my hyperbolic sort of contrarian stance, but I propose that what you're really saying there is that I can look in those models and those models look like the things that I learned in graduate school, right? We could think about a world where Claude Shannon lived before Isaac Newton, right? We could think about a world where the scientific method started with looking at flows of information in a digital sense, in a sense of entropy, and where we didn't have physical laws that described mass and energy units, or those came later. We started with physical laws that described flows of information, right? And that's what these machine learning models are really doing. And so the question that I have for you is, or the proposal that I have, I'm really going off my planned. I'm going to come back to all this. Sorry. Oh yeah. The proposal that I have for you is that there's a direct sort of isomorphism, a direct mapping between the concepts that we have in physics and the concepts that we currently have in database modeling. Okay, so I think it's not necessary when we talk about learning from doing pure database modeling. It's not necessary that our models learn new things that we haven't discovered before. In fact, that request of our models is something new that's never happened before. It's also not true that the machine learning models are a black box. They're a black box to us because we've grown up in a culture where we learn, where we think and we do all of our schooling, we do all of our research and all of our learning in the context of these physical units. But the concepts are there, right? So we can talk about, I'm sorry, I said it backwards. These are the physics, these are the machine learning. So we have all the basic concepts. Any physical law, I think, is built on basically these types of concepts. Conservation laws, locality. So what is causality? Causality is just conservation, local conservation, right? And so we can do non-local learning. We can enforce monotonicity. When we sit down and write scientific laws, we really think mostly in terms of pluses and multiplications, and those things really exist in some abstract form in different types of machine learning components that we can use. I don't really want to go through and explain these isomorphisms. I'm happy to do that offline, but the point I'm trying to make is that all those concepts exist. So we could look into machine learning models and see them as clearly as we see anything that's happening inside of physics-based models. We don't because we weren't brought up that way. Okay. Jonathan here? Yeah. Okay. Yeah, I'm going to stop there. I'm actually not going to do the rest of my presentation because I think that's kind of what I wanted to say. I was going to tell you about some experiments that Jonathan ran when he was doing his PhD with me back at University of Alabama that kind of showed how, yeah, let's do that. Okay, so.
You haven't offended us yet. You have to start doing that.
Yeah, well.
Well, some, when he said talked about insanity, I'm sure.
Okay, but that was
Okay,
nice.
so what I see a lot of happening right now in my own community, and there's a lot of people from a lot of different communities. I'm really sorry that I missed the introductions by everybody yesterday because I don't actually know where a lot of you guys, where you people come from. But in my community, which is hydrologic modeling, there's a really big push right now to merge physics and machine learning, right? And I think this is really fantastically stupid. Just fantastically stupid, okay? And I want to, I think the reason. Okay, and the reason for that is that we have no idea what the limits are on the information content of our data, and we have no idea on what the limits are on our information content of physics. We know that we can build data-driven models that have more information than physics models. I'm talking only about surface hydrology, only about the field that I know. I know this is not true in epidemiology, 100%. There's several fields where this is definitely not true. But in hydrology, we have not found an example where we can't beat the best physics models with machine learning. And so if you sit down and you're motivated to merge physics and machine learning, at this moment in time, you're not doing it for honest reasons. You're doing it because you understand physics, you're excited about machine learning, and you want to bring these two things together. You're not doing it because you found some limit of physics, and you're not doing it because you found some limit of the information content of data. And I'm saying this with complete confidence. I'm looking into your mind and knowing your own motivations, but really what I'm doing is I'm reading the literature. There's several hundred papers written about this, and there's not a single one of those that's been done it for sincere reason. So I'm going to give you this example where we tried to put physics into machine learning because, sorry, you just laughed at, but the reason was, and then we found out that it failed. And particularly the physics that we tried to put into machine learning was conservation of mass. So we have this sort of machine learning structure, which I'm not going to go through the math, but it's actually on this poster right there, if you want to look at it. And we embedded that sort of that type of mass conserving perceptron inside of an LSTM, and we ran the LSTM over some streamflow data and looked at what happens if you hold out extreme events. So our hypothesis was that we encode a symmetry into the LSTM. The LSTM is being used for streamflow prediction fairly successfully. We imposed a particular type of symmetry into the structure of the LSTM, and this particular type of symmetry causes the structure to conserve mass. And our hypothesis was that this will help for extreme events. So if we have this machine learning model, it's never seen a lot of rainfall before. What happens if you tell it, okay, now there's a lot of rainfall? It's not going to know what to do. It's never seen this before, right? So if you encode mass conservation into the machine learning algorithm, it sees a lot of rainfall, now it has to do something with that rainfall. That was the hypothesis. So we trained this thing, or Jonathan trained this thing. This was all Jonathan's idea, by the way, not this part, but the experiment part. I had no idea he was even doing it, mostly till it was done. So he separated all the data into different return periods, and he left out years with high return periods, trained on years with low return periods. And he found out that, yeah, you do lose some information. The blue are regular machine learning algorithm. Orange is the machine learning algorithm with mass conservation, but you lose a lot more information when you impose mass conservation onto the problem. So you open up the hydrology textbook, Chow, what is it, Praveen? 1989 or something? I don't remember.
Oh, that was 70.
70.
Oh, yeah, some late 70s.
Okay, so you open up the sort of hydrology textbook. Equation 1.1, I checked this, it's true, is conservation of mass. Everything is built on that. You impose that into a machine learning model and it causes harm to your predictions. So I'm not quite sure what physics we're supposed to be merging with machine learning, but it certainly isn't the foundational physics in hydrology, okay? And we know why that is. I don't know if this is interesting, but I'm going to spend 2 minutes on it because this was, again, Jonathan did this. It's 100% Jonathan's, and it was genius. We found a bias in the rainfall data between the eastern and western United States. We found this particular rainfall data set, and we calibrated a hydrological model separately at 531 catchments, and we found there was a strong bias in the eastern US and no bias in the western US. And we found that with one precipitation product, but not another precipitation product. And this sort of told us that there's a bias in the precipitation in the eastern US and not the US, but the western US for this one particular product. And then we ran the machine learning algorithm. And one interesting thing about this machine learning algorithm is that it's not trained per location, it's trained over all of the US. So it saw, in this case, it saw this data was biased, the same training procedure, same model saw all this data was biased, all this data was not biased, and then learned how to correct that bias, right? So why does mass conservation, what does it have to do with mass conservation? The point is that our rainfall data is biased. If you enforce mass conservation onto the problem, you're conserving wrong data, and the model is able to learn that, and it's able to learn that in heterogeneous ways. We broke this down both in space and time, and it's able to learn this, like, doesn't apply everywhere, it applies some places, it sees enough good data, it can kind of learn its way around this problem. So this goes back to this diagram I had earlier where a model is really a relationship between two pieces of data. That's what it has to be if you're going to do anything that I think can be called science. And the data is not perfect. And the question is that we have to ask is this. Right. What are the questions that we have to ask? I was going to frame this, I was going to try to do this Socratically and I messed it up. So in my mind, these are the questions that we should be asking, okay? We have imperfect data, we have imperfect physics, and you can only really marry these two things in two ways. One is you can, if you believe that there are universal approximators out there, then adding regularization to any type of learning algorithm on those universal approximators, all you're doing is regularizing the optimization. Okay, there's a lot of potential value there, but there's nothing else that you can do. You can't add new spaces of the function space to look through because these are universal approximators. So all you can do is chop off spaces of the function space that your optimization is looking through, and you could ask the question: does decreasing the density of that space, or actually decreasing the manifold that space lives on, does that actually help your optimization algorithm? So that's one question that we could be asking by adding physics models. The other question that we could be asking is, okay, this is the information content of our data. Let's pose this in a geometrical way. We have this envelope of trading data. We might go outside of this envelope, and can we do any regularization outside of this envelope? Really, these are the only questions that we can ask, that I can think of. I can't prove to you, but I can't think of any other questions that have any value. And so when we talk about bringing these 300-year, when did Newton live? 300-year history of science that we're all taught throughout our entire lives. Sorry. Okay, thank you. Yeah. Great. It's actually something in 50, right? He was in the 1770s. No, it doesn't matter. Okay. Anyway, so if we want to bring this very rich tradition that we have and we all know very well into this sort of age of sort of really unexpected advancements in these universal approximators, I think that, well, certainly I know for a fact because I was here. When we had the last meeting here, no one believed in machine learning. That was not too many years ago. There was just no appetite for it. The way I like to tell the story is that we weren't, well, it doesn't matter, but no one believed in machine learning. Yeah. I don't want to attack anybody. So expose the real source of my bitterness. But our attitudes have completely changed. I think that you would be special if your attitudes on machine learning hadn't changed in the last 4 or 5 years, and that is the pace of acceleration is just it's way different than the pace of acceleration in physics. But we really have these two things, and they probably will come together, maybe. But if they do, I think we should be asking coherent questions. What does that have? So when Uwe asked me to give this talk, he asked me to talk about the relationship between academia and big tech. And so let's try to shoehorn that into what I'm talking about now, right? So what does that have to do with academia and big tech? Okay, so what is happening in machine learning, right? What has happened over the last few years? I see it like this. This is my version of what the situation looks like. We've been playing with these things for a long time. Then we started using, I don't know if this is temporal or just like a conceptual flow of ideas, but we have the ability to take our physics models, emulate them, estimate the parameters, do some post-processing, ensembling. We can add machine learning-based cloud resolving physics around dynamical cores of weather models. We've been doing this for a long time, right? We can marry AI and physics by adding ML-based parameterizations to our models, and maybe that's actually closer to this thing of adding cloud resolving physics to weather models, maybe, depending on how you do it. Certainly, this is what I showed in the second experiment that we just talked about. And then we can do this other thing. We can build AI models, AI first models. And this is what I've really been looking forward to the geoscience community doing for a long time. The way I envision this is you would build a conceptual graph, a DAG. I guess I gathered from comments yesterday, I got here late, but then we talked about DAGs yesterday, so I'm just going to kind of guess. But you could build a DAG and you could learn the edges of that DAG, right? The edges of the DAG could be either learning algorithms, universal approximators, or they could be prescribed relationships based on physics or concepts. But anyway, we're dealing with these graph models. And I would just point out that there was a series of papers in the atmosphere weather modeling community in late 2022, where they really advanced this graph modeling concept in weather forecasting. I think NVIDIA, Microsoft, and Google each published one slightly better, and all claiming to beat ECMWF. I don't want to get into whether the root mean squared error is a good metric for precipitation patterns in weather forecasting. It's certainly definitely not. There are problems with that, but the point is that there's really a lot of people are just have started these projects a couple years ago, and they're really just starting to become finished to where they're getting results. I was trying to get the hydrology community to work on this kind of thing a long time ago, and as far as I know, there's still no hydrology groups building AI first model, no true AI first Earth systems models. I talked with the Klima project, which would be the closest thing I know of about this, and they are vehemently against building AI first models. They want to put they really want to put AI into their physics models, and that's the most advanced sort of full Earth system model that I know of. So I think we're not doing this, but this is still old. So now this is old. Now what's happening is in AI, as we're using these foundation models, these semi-supervised models that have something like an ontology, or you can imagine some ontology underneath them. So there are many groups in tech building these, what they call geo-foundation models. We missed the generation by not taking action on these things. Tech is building these now. Actually, we got funding at Google to build this, and which I have been aiming for years, and now I'm completely unexcited by it because the future are these geo-foundation models. What I'm talking about is how are we going to build models that see all of the data in the world, and what I think these models are going to do for us is they're going to provide platforms for hypothesis testing. So it's really hard for us to do hypothesis testing with models right now, because if I have a hypothesis about a particular subcomponent of a model, and I switch that subcomponent out for, I test my new hypothesis with some old version of that subcomponent, the model may be better, it may be worse, I might get a positive or non-positive result of my hypothesis test, but I don't know how much of that is because this hypothesis just agrees with the rest of the errors in the model or disagrees with the rest of the errors in the model. What I hope to see is that if the community can start to build these giant database models that are as free as possible from conceptual understanding, that it will provide a platform for us to impose our conceptual hypotheses onto and test them in a way where we can train the whole thing around them and we can kind of isolate the effects of individual hypotheses. That's my hope for the future. But in order to see whether we can do anything that looks like that, whether we can actually start to use models to do real hypothesis testing, which by the way, right now we can't. Our models are black boxes. There's no way to take a physics model and turn it into something that's not a black box from the perspective of hypothesis testing. What I'm proposing is that there should be a way to do that with machine learning. I think the real black boxes are physical models and the white boxes are machine learning models, because you should be able to impose individual hypotheses onto a data-driven model and then learn your way around them so that you don't have this compensating error structure problem. But in order to get there, we need to build these giant AI models that can sort of represent the whole system, or at least represent all the information content in the data that we have, so that we can understand where the limits of that information content and then start to correct those real limits. What is it going to take to build these giant models? At least 8 figures, at least tens of millions of dollars. I don't think there's any hope of building it for less than that. So what would I like to see happen? I would like to see the funding agencies, NASA, ESA, NSF, DFG, whatever, start to set up centers to do something like this. And as far as I know, I've been out of the loop for a while, so maybe it's happening. But as far as I know, that's not exactly what we're doing at the moment. Anyway, thanks. Yeah.
Thanks, that was awesome. Great, we have time for questions. Pushback, reactions, and
Yeah, I'll start with a pushback in a certain sense. And it's probably a pushback that you'll find okay, because it's on the engineering side. Sure, our models have mass conservation, but anyone who actually used them for anything, even 20 years ago, we bias corrected them with rogue mass conservation. We knew that wasn't like a thing, we just didn't know how to do it differently. Right?
So yeah, I agree, completely agree. And data assimilation works even though we know it. I remember going to these AgMIP conferences 15 years ago when the ag models were just starting to use data assimilation, and all the modelers hated it because it broke their mass balance on the carbon balances. Now, of course, they all use data assimilation because you have to get a good answer. And we've just accepted that we break mass balance. And so my question is, like, obviously there are real answers to this, but my question is, if you're breaking the basic concept of your model, how much do you trust anything that you build on top of that? I mean, maybe you can trust the mass balance. I hate seeing myself. Maybe you can trust the mass balance in the little. I got it. Nice.
It is very little, yeah.
In the little subcomponents, and you don't have to trust it in the overall. Maybe that's a possibility. I don't know. I'm not saying I wrote one of these articles, these white papers, sort of criticizing hypothesis testing with big models once, and I got an email from one of the scientists. I can't remember her name anymore, but she was one of the scientists that the Republicans in the U.S. Congress called to debunk climate change. She was really excited about my paper, and I don't want to give that impression. Like there's a lot of information in our models. It's really, really good information. Like we're doing a really good job given the limits of our data, of the information in our data, the errors in our data, and the limits of our ability to measure everything that we want to measure, and the limits of our theory. The main limit of our theories being that in order to get the model to run, you actually have to prescribe relationships for everything that's going on. You can't actually leave one out. Otherwise your model doesn't compile, it gives you nonsense or whatever. So I don't want to give the impression that I don't believe the models. I'm just saying that if we're talking at the level of looking for and realizing that there are gaps in the information content of our models, and we found a lot more information in our data, I'm trying to phrase the way that I would ask these questions in this reality. Yeah. I don't know if that. Yeah.
one more question. Yes, Peter.
Yeah.
And so that was very thought-provoking. Thank you. So that the mass conservation example was made very clear what you meant. Still, I would like to argue that it's really a lot more complicated than this, and it really depends on. It changes from maybe from field to field, from situation to situation. So, in a way, what you're saying parallels what happened at the beginning of deep learning with computer vision, where also the idea was we have all these like hundreds of features which are kind of man-made, like you put in these before you analyze a picture, whether it's a cat or a dog, you make all these transformations and filters, which we impose as humans to make the thing better. And now we can learn our way around them, and they actually maybe they just introduce bad biases, not good ones, so we just ditch all of them and learn everything.
Yeah.
That's how it started. It worked much better. But then later, partly because of these enormous financial and energetic amounts, people like Max Welling, for example, they started to impose on those networks, and I would say those are physical constraints, like invariances, like rotation invariance, translation invariance, and they got them even better.
Yes.
And then it went back. They actually went back to the physics, very simple physics. Just we know that if you rotate a picture, it's still the same picture, and got things better. So then they did use this very simple principle from physics to improve it even more, and that was actually quite recent. This year, like in the last 5 years. So. I think that it's always going to go back and forth between universal approximation, and where you get more data, you can drop more and more biases, and that's nice. But on the other hand, I think there will probably always be like first principle ideas, which is something, well, maybe we should impose this, and maybe it'll get even better.
So
That would be my view. It's like it goes back and forth.
I would say even convolution, because there is also a translation of invariance. That was there from the beginning. So I would even say it's that clear that it came later, even at the beginning, when the convolution.
Because they use convolution, which is already like using
It is invariance.
like the right model in a way.
Exactly. Yeah. Sorry.
yeah, so I just want to say that this is exactly my point. What I'm really asking for is a period of time where we build the second part of yours. So there are 3 stages in what I heard you just say. The one is where we are trying to impose our concepts on little models and trying to, because that seems right. And then we build the big models and they just learn their way around it. And then we start imposing concepts on the.
Yeah. So I see kind of a cycle.
Yes, and that's exactly what I would like to see. I would really like to see our community, the geoscience community, start to make the investments that we need for that second phase, where we build the big models so that we can start to learn our way around these problems, so that we can start to actually find the limits of the information content in our data and our theories, and then we can start to see where we can impose. I think that it's hard to get to that 3rd stage without doing the 2nd stage, and my opinion is that we need to think about how the money's spent in order to do that 2nd stage, because the big models are really, really big.
Let's thank Ray for this.
Really